I have to say that a large number of civil infrastructures like roads or railway tunnels require inspections, and the inspection phase is a very important one to decide on timely and appropriate intervention. That's to avoid long-lasting interruptions that can cause a lot of social and economic impacts. That's just something that I live where I live in Napoli occur once a year. That's a tunnel 100 years old that has a problem with maintenance, and I am locked in a traffic jam in Napoli going to my office in the university. My presentation has a content that is summarized in these slides. You see that I will show briefly some experience with conventional monitoring on old and ancient tunnels. You will see an overview of new technologies available, and I will underline the need for calibration. And I will give you some overview of research carried out in Napoli University about the segmental prefabricated lining. And finally, I will have a look at reliability and longevity of sensors used in the monitoring. I started my early experience in monitoring tunnels with some collapse. Here, that's an important tunnel along the motorway from Napoli to the south of Italy, and the collapse generated by the failure of earth retaining wall here and produced a lot of cracks. And monitoring for 1 year revealed that basically there were no movements going on, and that the cracks were just moving yearly with the temperature cycles. So at the end, it was concluded that it was safe to cover again the tunnel and just to seal up the cracks. Similar experiments were carried out also in very ancient tunnel, and here you see an experience carried out in the Roman theater of Ercolano, buried by Vesuvius eruption in 1710, where a lot of cracks were present in the volcanic soft rock where the theater is buried in. Again here, monitoring for a couple of years showed that there were no movements going on, and the theater was again open to the public for visit. I was also involved in inspections and surveys on Roman ancient tunnels. We have 3 very old tunnels in Napoli excavated by this architect Russo, and I have no time to go into detail, but it was a very nice case. And here you can see a fantastic overview by the balcony, where you get through passing under the Posillipo Hill with these 600 meters Roman tunnel excavated in tuff. Recent updates in codes and regulation in Italy have occurred. They basically have introduced a list of new technologies available for inspection and surveys, like georadar and other things. And they ask for cooperation with university and research institutions in order to have reliable results out of these technologies, because these technologies need interpretation. Just to give an overview taken also by the literature, I tell that from a long time is available the light detection and ranging technique, for instance, based on laser use and with very good mapping algorithms. What we can have is a deformation field in the tunnel by comparing 2 subsequent images obtained by the laser scanner. And in this case, just a very small defect simulated by a 6 millimeter thick wooden stick was detected with this algorithm. The laser scanner has, of course, its principal use into the survey for getting the geometry of even complex tunnel, like in this case was done in a natural tunnel in rock in Brazil. The digital model that they obtained by this 3D laser scanning was put into a PC, and a 3D printer was used to print out a model of the tunnel at lab scale. And this model was load tested in the lab, And in this case, digital image correlation was used, which is another technology very widely diffused today to measure the strains in this prototype. Among one of the most successful recent advance is the infrared thermography. Of course, we can have different types, active and passive. And in this paper here, we find a very intelligent way to use the infrared technology, because it's basically based on the fact that during the train stop hours, we have a natural decrease of the temperature inside the tunnel, and this temperature decrease provide an higher resolution into the possibility to detect unhealthy concrete and understanding the difference between unhealthy concrete and an unhealthy concrete. This is a way to use passive thermography in an intelligent way. Of course, defect in an healthy concrete mass via infrared needs calibration. Calibration that can be carried out, as shown in this nice paper by Akage et al., by using finite element calculations of the thermal conductivity process involved in such a situation. Here we have this research carried out in my university since a rather long time, and I was involved in line 1 and line 6 underground network. Here you can see just a picture of a famous station designed by an international archistar, which is Boris Pedreka. This is very close to the sea here. That's the line 6 project, while the line 1 is in the city center below a number of buildings. I was involved into monitoring initial loadings and internal forces in the lining, and I just had experiment on the segmental lining used in this tunnel. This segmental lining has a crucial design aspect in the gaskets, the O-ring gaskets that allow to prevent the water leakage inside, because, and this picture is not taken by Napoli underground, we know that the one of main defect in this type of tunnels is the possibility of having water leakage inside the tunnels, and that has to be avoided. In this case, we just monitored the strain in the lining in the initial stretch of the line, which was below the groundwater table and in sandy material. That's part here, and we load tested segments of the reinforced concrete segment in order to have calibration of the gauge response with given external loading. And this calibration allowed reliable interpretation of the gauge result inside the tunnel. The tunnel, when finished, appeared like this, so you can understand that was really no water leakage occurred in this situation, and it was a very, very good news. When we went to interpret this data, we discovered that the simple attempt done by using simple beam theory was not successful. Bending moment and axial force derived by this theory from strain gauge produced large tensile axial forces, as you can see here in two of the rings instrumented, and this was of course not physically possible because of the segmental nature of the lining. So we did a second attempt later with a rather complex procedure that I have no time to get through, and we derived the internal forces in the lining by using the measured strains by the vibrating wire gauges, and the result was indeed successful because we really obtained the axial force distribution in the lining that were very similar compressive and were very similar to expected theoretical value by some simple end calculating results. We had ring 3 and ring 4 here. Finally, well, more details on the procedure is available on this paper on the American Journal of Civil Engineers. I was involved in the line 6 too, where you can see here some of the picture. It was a challenging work with 50-meter deep excavation close to existing building, and here you can see the tunnel. And the segments were the same type, installed vibrating wire gauges inside in the same way. The procedure was pretty the same. We could benefit of a wireless system due to the technology available, and we could do a lot of interesting check on the quality of readings, like for instance the overall equilibrium of the TBM machine, which of course exert a pressure to move on, and this pressure was clearly recorded by the vibrating wire gauges. We did in this case finite element model of the problem, and we used the epsilon, the strains calculated and the strains measured with the trial and error procedure in order to derive the full axial force and bending moment inside the lining. And the operation was quite time consuming due to the time needed for the to carry out the trial and error procedure with a lot of variables inside, and finally we get a very satisfactory result. Let me tell also that vibrating wire gauges are vibrating wire gauges. I have a lot of experience with this type of gauge. They can be considered old technology, but they have given me always the proof to work properly, even in conventional tunneling, and I have published a lot of papers with interesting readings. The longevity and the reliability of these sensors is very important, and I just want to tell you that when I started as a PhD student, I installed 30 years ago, more or less, I installed these gauges inside a deep foundation project in the south of Italy below a cable-stayed bridge, and about 30 years later, the sensors are still there and working with a rather extraordinary performance. So I think that these kind of gauges are still on the market and can be reliably used for long-term monitoring. And I go to conclude, existing tunnels require inspections and controls, and new technologies are useful and available, but engineering judgment is needed. Because when we have to deal with the tunnels 10 years old, 100 years old, and as I've shown you also maybe 2000 years old, not a unique solution is possible for all purposes. Artificial intelligence application can be very useful to support engineering work, maybe for instance, in my presentation for guiding the trial and error procedure, which was really time consuming. New sensors are available and new transducers are available, like MEMS, coupled with the LoRaWAN technology, but these can substitute old sensor and old technologies only if they prove to be reliable in the long term, because the long term is needed for maintenance problem. And finally, last but not least, I would say that if you detect a defect or a damage, not an easy task as for the engineer to assess a correlation between the performance of the tunnel and the defect, because if you have not clear in mind a correlation between these two things, the detector of the damage is not useful for establishing a strategy for maintenance. That's all. Thank you for your attention, and I leave the floor to the question and answer session.